All right, we're going to reconvene here. So we're moving to our next part of the program where we're going to hear from some students who have been working really hard on their science and their presentations, and they're fantastic. Before I do that, I want to introduce Jason Cervenik, who's our Director of Education and Outreach Programs here. And we do excellent science here at the center, but just as importantly is the communication of that science and the outreach of that science, so to make it useful to people and to educate them. And Jason has done an incredible job in his, 7-8 years here, expanding our programs into something that the university can really be proud of. So, let's get Jason.
Thank you, Ian. So we'll have a chance to hear from some students now. We're going to have 2 undergraduate presentations and 2 graduate student presentations. One of the things the center prides itself on is the work that students and postdocs do in both the laboratory field and our outreach programs. And a lot of these experiences are considered integral parts of both the students' education, but also the contributions the Byrd Center makes to cutting edge research. While a majority of these opportunities are funded by federal grants, and most of the funding for our research comes from the National Science Foundation, NASA, and NOAA. A number of those opportunities are not always possible, and so we do have friends of the Byrd Center that are able to step up and provide opportunities for students that otherwise would not be available. So I want to showcase a few of those before we go ahead and hear from the talks today. Thanks to Pam Theodotou, our media specialist, for putting that together. The first two presenters today are both undergraduates who've received funding from the Brecher-McKenzie Scholarship. This fund was set up in honor of 2 well-known Byrd Center members, well-established long-term Byrd Center members, Henry Brecher, who was here earlier, and Gary McKenzie. It was an endowed scholarship that provides funding for travel, registration costs for meetings, research materials for laboratory supplies, publication expenses, anything a student needs to make sure they get their research opportunity to the fullest and takes it to completion. And so we were able to get this endowed a few years ago, and the 2 speakers you'll hear today have received funding. My own group, a number of students have received funding that's allowed them to go present at national conferences. Okay, the first presenter today is Ryan Benefiel. He's with the School of Earth Sciences. His advisor is Audrey Sawyer, and so he'll be kicking off today's presentation. So come on down, Ryan. Right now, we'll see it.
So, good afternoon, everyone. My name is Ryan Benefiel, and today I will be discussing my research on phosphorus retention in agricultural headwater streams.
Technology.
You might be able to
Lock down.
that work.
Give us a second.
There we go.
All right, so.
Thank you. Awesome.
There you go.
Thanks so much. All right, so back to the presentation. So a little bit about myself before I begin. I am a fourth-year undergraduate student in the School of Earth Sciences, and I'm specializing in hydrogeology. So I began this project a little over a year ago with my advisor, Dr. Audrey Sawyer, and I'm really excited to share with you guys what we've been working on. So we focus our research in Northwestern Ohio, but this problem can be applicable to many different parts of the United States. So why exactly is understanding the transport of phosphorus so important? So we know that phosphorus is an important growth factor in plants, and this is also applicable to algae. So if we have a high influx of phosphorus, such as from agricultural runoff, then we can have the formation of harmful algal blooms, or HABs. And what these do is they remove oxygen from these large bodies of water, which makes them anoxic and makes them uninhabitable for other types of life. And so this can create what you see up on the right, where you have many different species of fish and killed because of the anoxic environment. So focusing back in on Ohio, what we've seen over the last several decades is that although farming practices as a whole have improved, there's been no real improvement in the export of phosphorus to Lake Erie. And so from the Ohio Lake Erie Phosphorus Task Force, we know that over 50% of the phosphorus load to Lake Erie comes from these croplands. And this can be really frustrating to these farmers who are working hard to reduce the phosphorus output, but seeing no real results in Lake Erie. So if we look at these charts that are up on the screen, we can see dissolved phosphorus up on the left and phosphorus that is attached to sediments on the right. When looking at phosphorus attached to sediments, we can see that it stays relatively the same and even decreases a little bit over the last few decades. But when looking at dissolved phosphorus, we can see a big jump in the amount of dissolved phosphorus load in Lake Erie over the last several decades. So this is what our research focuses on, is decreasing this phosphorus load by quantifying the transport of phosphorus to better inform farmers of wastewater treatment options. So how expansive actually are these agricultural streams? So here you can see a Google Earth image of our study site. It's a small little 200-meter stretch of a headwater stream that we focus our studies on. So if we zoom out just a little bit, you can see our study site becomes very small, and we can see some neighboring streams that kind of start to coalesce. And then zooming out even more, you can see some nearby cities and some of these larger rivers that these headwater streams feed into. And you can see that our site becomes quite small. Zooming out even more, you can see that we really can't see our study site anymore, and really even these cities start to become small. We actually have to zoom out once more to even see the large body of water that we were aiming to study and that our headwater stream feeds into, which is Lake Erie. So you can see how specific our study site is compared to the vast network of headwater streams that we have in northwestern Ohio throughout these croplands. There's actually over 30,000 miles of these headwater streams throughout northwestern Ohio, and almost all of them feed into Lake Erie at some point. The real problem with this is that there's currently no major studies being done on these headwater streams. Most of the effort is focused on these larger rivers and bodies of water. So while these focus on what the phosphorus does when it gets to these locations, we want to focus on how the phosphorus actually gets there. And so we can look at several factors to kind of quantify the transport of phosphorus. The first being absorption and desorption. So absorption is basically when particulate phosphorus in these streams will stick to fine particles. And this can cause delays in the transport of the phosphorus downstream when these sediments settle out of the downstream flow. Another factor that we're looking at is the uptake of phosphorus into vegetation and biofilms. So as stated earlier, plants and biofilms love phosphorus because it helps them to grow. So they will uptake this phosphorus out of the solution and use it for growth, which will then cause delays in the phosphorus transport downstream. And so we know these factors affect the rates of phosphorus transport downstream, but how exactly do we measure these? And that is through a method called tracer injections. So this is a way that we can put a concentrated solution into our stream, which allows us to see how that solution moves downstream and affects the downstream flow. So there's two main factors to this. There's both a conservative and reactive tracer. A conservative tracer is a substance that we can put in the stream where we know it will not react with anything else in the stream, and gives us an accurate measurement of how our solution is moving downstream. So in this case, we use salt because we know it won't react with things that are present. And so we measure this using sensors that are at each of our sampling locations, and those measure the specific conductivity of the salt in our solution. So the next part is the reactive tracers, which are the things we were actively studying. So the first is phosphate. This is what provides the phosphorus that we were trying to see how it moves through the stream. And we also have our fine particles, which in this case is day-glow pink pigments. And these are to simulate sands and fine muds that are present in the stream. And we use these particles because they are much more accurate to read in the lab as far as particle counts. And so using both the measurements from these phosphate levels as well as the conductivity from these salts, we can create a model that allows us to see the delay in travel times of the phosphate. And so this gives us something like what you see here, which are called breakthrough curves. And so these breakthrough curves allow us to see how the solution is moving through the stream at these different stations. So up top, you can see a breakthrough curve of our conservative tracer, which is salt. And on the bottom, you can see these curves for the conservative tracer plotted with the measurements of our phosphate levels at these different stations. And so there's three main things that we're looking at when we're looking at these breakthrough curves. So the first one is the lateral shift in the arrival times of these curves. So you can see as we move from stations 1 to 4, we have this shift in the arrival time of our solution, which we would expect because it takes longer to reach these stations. And so the next is what we actually use to quantify that delay, which is the spread in the tails of these curves, as well as the decrease in peak height. And so these things show us that there is some sort of immobilization of the phosphorus going on that is causing this delay in travel. And so these tracer injections are the main point of our studies, but I have a much more specific role in our group's efforts. And this is to quantify the relationship, the absorption relationship between these particles and our dissolved phosphorus. So as I stated earlier, the absorption is when the particulate phosphorus will stick to particles that are in the stream. And so my job is to quantify how this relationship actually works and how much of the phosphorus is sticking to these particles. So since these particles are relatively new, there's no real studies around it as far as how much of it is sticking. And so in an ideal world, there would be no relationship between them and they would not react. But we know that science is never this easy, so we have to quantify this to account for it in our models. And so through a series of experiments, we can quantify how much of the phosphorus is adsorbed given certain phosphorus concentrations. And that gives us something like what you see up to the right here, which is called an adsorption isotherm. And this basically relates the phosphorus concentration that we are using to the amount of phosphorus that is adsorbed to those fine particles. So this figure that you can see up on the screen is a study that was conducted in China on a various amount of sediments. And this is what we hope to replicate after the conclusion of our experiments. They are still in progress, so we don't actually have any figures made yet. So we hope to accomplish what these scientists in China have accomplished. So that is the main goal of our studies. I would like to thank my advisor, as well as my graduate student advisors, Hannah Field and Devin Matthew, for all their help, as well as Byrd for allowing me to speak to you all today, the McKenzie-Brecher Fund for funding my research and allowing me to do awesome things, as well as Michelle Cook for all of her help facilitating that. So thank you.
For questions, Ryan?
Yes.
What's the ultimate goal of the research? What do you hope to take the next step from this?
So we could, yeah. So the question was, what is the end goal of this research and what can we accomplish by learning about the travel times of phosphorus? So once we learn how this phosphorus is moving, we can actually inform these farmers on different practices they can take to reduce the phosphorus traveling through these streams and out to larger bodies of water. Yes.
What is a biofilm?
So the question is, what is a biofilm? So this is basically a thin layer of microorganisms or biologic, some kind of biologic film that forms on either the sediments or the plants that are present in the stream. And these will uptake some of the phosphorus that is traveling through the stream. Yes.
You mentioned you're in your 4th year of your undergraduate program. What is your ultimate or your initial career path that you see?
So I'm still working on that currently. If any of you guys have a geoscience background, I'm going to GSA, their national meeting. I'm actually flying out to Oregon tomorrow morning to go to that. So hopefully I can, I'm looking to go to grad school after this, keep working in hydrogeology, and then after that, possibly a career in environmental consulting.
Any other questions for Ryan?
Yes.
So if I got this right, you're mostly looking at the transport of the particulate phosphorus, salt phosphorus as well?
Yeah, so the dissolved phosphorus is actually those measurements that we were getting. So when we were measuring our phosphorus, we're taking physical water samples out in the field, and then we're taking those and we have a scalar machine, which will read those dissolved phosphorus levels from those actual samples.
Any other questions? Thank you, Ryan.
Thanks so much.
Okay, our next presenter today is also an undergraduate, Kat Zick. She's an environmental sciences major, and she's being advised by Dr. Barry Lyons.
Hello, my name is Catherine Zick, and this is my undergraduate research presentation on lead in Ohio State University's drinking water. So to begin, a quick note about me. Hello, as I said, my name is Catherine Zick. I am an environmental science major here at The Ohio State University. My specialization is in water chemistry, and I am in honors and scholars. And I'm doing my honors thesis through the School of Earth Sciences. And so to begin with the presentation, lead has a myriad of health effects that are very widespread throughout the body. And there are two main ways that humans can be exposed to lead. These could be through the environment, which could be through the air, through the dust that we're interacting with, or through lead paint. And there is also through the water, which this presentation is focusing on water. So at higher levels, lead can cause damage to the central nervous system, though at lower levels, lead can still be very damaging. Especially in children, the effects that are most well known are the neurological effects, such as the decreased IQ, the increased risk of attention disorders, decreased academic performance, increased impulsivity, as well as sometimes even delayed puberty. In adults, low blood lead levels can also cause hypertension, and most alarmingly, even an increased rate of spontaneous miscarriages. And we discovered all of these health effects after building city after city out of lead pipes. Lead is an element that is so integrated into the practice of our plumbing systems that the word plumbing itself comes from plumbum, the Latin word for lead. And because of this, there are several different policies that are in place to keep people like you and me safe from lead poisoning in our drinking water. Most notably, there is the EPA's lead and copper rule, which was first established in 1991 and established an actionable limit of lead, which means that when greater than 10% of the buildings in an area have 15 parts per billion or more lead in their water, parts per billion is also micrograms per kilogram, then this will trigger a corrosion control response, which could be in changing the water chemistry, in corrosion correction treatment, or in replacing lead pipes. There are also some revisions that were proposed but not yet enacted in 2019 that would, if accepted, make this actionable limit be the limit for any single building, meaning if any building surpasses 15 parts per billion, this corrosion control response would begin. Though this has been a very controversial rule among experts because there, strictly speaking, is not necessarily a safe level of lead to be consuming. And so there are a lot of debates among experts of whether or not this is enough. The CDC still maintains that there is no blood lead level, especially in children, that can be considered safe. And now I keep using the phrase parts per billion. To go more into detail on that, a part per billion is 1 microgram per kilogram. And to put this into perspective, this is the equivalent of a ratio of about 3 seconds to a century, or about a half a teaspoon of water into an Olympic-sized swimming pool. This goes to show that you cannot tell if there is lead in water by the taste or by the sight, and that we have to take some very serious sampling protocols to make sure that contamination is avoided, and could go to show just how potent of a toxin lead is. And so the purpose of this study is to determine different factors that could put buildings at a risk of higher lead concentrations in their water. We also like to compare the results on campus with existing policies surrounding lead. So there is the lead and copper rule, which I recently explained, that has established the 15 parts per billion actionable limit, though this is often not well communicated to the public if this actionable limit has not reached what the apparent limits of lead are in drinking water. And there's also the Department of Public Utilities lead service line interactive map, which is pictured off to the right. A lead service line is a portion of the pipes that feed to buildings, which go from the city's connector valve to the shutoff valve of the house. And this is something that anyone here, provided you have a Columbus address, can check if you have a possible lead service line or galvanized service line. Here, this map, we have focused on the campus region. You can see the football stadium on the far left for some perspective. And this can tell you whether the blue dot is a lead pipe or the purple dot is a galvanized pipe. And a galvanized pipe is a pipe that has been coated in zinc that is often impure and can contain lead, or my apologies, is often impure or can contain lead and may sometimes be soldered with lead pipes. And at first, it may appear that the university has none of these dots and is in great condition. However, upon closer inspection, the university is a data hole. There is no data to reference for this. And so one of the aims of the study was to get what the general levels of lead were for an area in which we do not have an idea of what to expect. We'd also like to compare the lead in the water from Ohio State University to the alternatives for drinking water on campus, such as the bottled water that can come from vending machines here or in the campus cafes, as well as to the other regions of Columbus. And so this study design was by taking 20 buildings across the regions of campus and also across a variety of ages. Here you can see the map of sampling sites that define the north, south, and west/medical regions, with the Olentangy River being what runs straight down the center. And again, for reference, the football field slightly off to the right. And these buildings were utilized random daytime sampling, meaning that we would come in and at a random point throughout the day, when the people who are professors and students would be interacting with this water, and take the first draw water from the tap. There were also 7 bottled waters that were chosen from within these sampling locations that were either at vending machines or at campus cafes. And since lead is everywhere, lead is pretty much everywhere that we have looked for it. It is in the dust around us, and this can make sampling a very complicated procedure. And so trying to make sure that the samples are not contaminated was a very big portion of the study. So we used Teflon bottles because Teflon less readily holds onto other materials, which were acid washed in a clean room, and the samples were not filtered, which can introduce additional lead contamination into the sample. We also utilize the clean hands, dirty hands method of trace element sampling, which is a 2-person method of sampling, in which case we make sure that only the person who has not touched anything else and is using very clean gloves is touching the sample, so that there is no other sources of lead being deposited onto the surface of the bottle. Moving on to the results of the study. Here you can see the lead water concentration by the different groups that were surveyed. So these are box and whisker plots, meaning that the averages are the X's and the boxes are the middle 50% of the data. The bars also represent the extremes of the data, so the range, the high and the low. So upon first glance, south and west have decently similar averages, as well as comparable quartile ranges, the middle 50%. And this compared with north, the north is a bit higher. The north was not only higher overall, just having slightly more parts per billion lead in most samples, but also had the presence of an outlier at 5.5 parts per billion that was higher than most of what we'd seen elsewhere. When comparing this to the bottled water is the thin black line towards the very bottom of this graph. this was statistically significantly different. The bottled water was all below the detection limit of the instrument used. The detection limit is posted off to the right at 0.002 parts per billion, or 2 parts per trillion, which is very exact. And this is the limit at which we can say that we're confident the detection limit and the detection limit is different from a laboratory clean value where we have done our best to minimize the amount of lead in every possible way. And so since the bottled water was all below this detection limit, we have marked that as 0 lead. And this is significantly different than the tap water on campus. Though for some perspective, while saying that the bottled water is significantly less than the tap water may immediately seem alarming, I can assure you that the 50 parts per billion actionable limit is way through the ceiling. So this would be up through the next floor. And so while it is different, it is not a large cause for concern. You can also see here that we did the lead concentration vary with building age. And this is not because we'd expect to see a very strong correlation here, but because in 1986, the EPA banned new pipes from being installed with 8% lead or more. And so here, what we expect to see could be a difference between the newer and the older, because we do not have the data of what is lead and what is non-lead pipes. And so because we are still in the early stages of the study and we do not have a ton of data, we cannot draw strict conclusions yet, but here's what we have so far. As well as the lead versus phosphorus concentration. Phosphorus is phosphate contents is very important to talk about with lead, because phosphate is typically a corrosion control additive in water, which will over time form a protective layer around the inside of a pipe, which can stop the water flowing through it from physically touching the lead pipe, which can make the levels of lead in the water less. And what we are expecting to see is less a strong correlation between the two, but more what we see is sort of a mystery. We would expect that since supposedly all of campus comes from the same water source, we would expect that it would all be rather similar at around 300, a little bit more parts per billion of phosphate. However, this is not really what we see, since there is a smaller group of samples that are concentrated around the 100 part per billion range, which is not exactly what we'd expect to see and could be an additional factor that is causing variation in these samples. And as you can tell, there are a number of unknown variables that seems to be a constant throughout the study. So we're not sure on campus what the composition of the service line is. There are not very well accessible renovation history records. And since the building is so large and there's so many people in it, we're not sure of the recent water usage here. And so moving on to the conclusions, the evaluation Department of Public Utilities map. So while we are not sure what the different types of pipes were that we were sampling from, luckily everything was well below the EPA's actionable limit. And so there is no immediate cause for concern here. We also saw that the bottled water found on campus had a statistically significant difference from the tap water, so that the tap water was considerably higher, and a lot of the tap water samples, a lot of the bottled water samples were very low in lead. And as I said, there are many different variables in the data, which we're hoping to mitigate in the next round of sampling. So some of the future steps of the study are to expand the reach to 80 to 120 locations around the city of Columbus. So we are also going to adjust our sampling methods to better adjust the proposed guidelines for the lead and copper rule that have not been accepted yet, to hopefully get a more accurate view of the range of lead values that can come in a single building, as well as we are going to evaluate the lead service line map as an indicator of lead levels. Since, as I said, with campus, we were simply taking a sample to see what we could find, since we didn't have any idea of which types of pipe we were looking at. But here we will have that data available to us. And so in the future steps, a lot of these unknowns we're going to be able to better know of and account for. So the composition of service lines, we will have the data for. We will also be able to ask the homeowners if there's any recent renovation history, and we can ask them about their recent water usage. And so we are hoping to get some more data that we can make better comparisons between in the future. So I'd like to thank the Byrd Polar and Climate Research Center and the McKenzie-Brecher Fund for support. I'd like to thank the University Honors and Scholars Office for their Honors Enrichment Grant, as well as for the incredible team in the lab that I am in for helping with chemical analysis and sampling collection, and my mentor, Dr. Barry Lyons. And thank you all for listening.
Any questions? And just a reminder, if you are on the stream, the Q&A button at the bottom is how you can go ahead and submit a question.
Yes.
So what are some areas of Columbus that you'd like to look at next for lead dissemination of water? Are there any specific ones that you are interested in looking at, or are you just going to stay around?
Sorry, could you repeat the last bit?
Sorry. Are you planning to like what other neighborhoods of Columbus are you looking at in terms of what the lead concentration of water is, or are you just going to stick around the university area in order to get a better idea of your greater on-campus lead dissemination?
So the question was, what are the areas of Columbus that I'm looking to do next, and what is going to be my focus if it's still university area or comparing the two? And the answer for that is that there are no specific areas that I am looking to sample. I am more trying to get a very large sample that is general and can tell about Columbus in general. And though this will eventually likely be skewed more towards the university area, since a lot of the people that I am interacting with on the study and who are able to help recruit people whose houses we can walk into and take lead, it might end up that we have more samples in the university area and the areas north, directly north, south, and west of this, east of this. That may be and what ends up happening, though that is not the specific goal here. Thank you for your question. Yes.
Great talk, thank you. Do you have interest in measuring lead in any other media, environmental media, like soils or house dust, or are you going to focus strictly on water?
While right now my interest is water, I think that lead in other places are very interesting. I'm not sure if within my undergraduate career that would be feasible since I'm a senior. I was doing some work towards the earlier time of the pandemic, not that I was a large part of, that I was grinding up soil for, soil in the lead in soils of Columbus, though I'm not sure what part of the research process that is in. Again, that's something that I was a lot less involved in than this. Sorry, I'm not sure if I repeated the question. The question was, are there any other environmental places of lead that I am interested in, such as in dust or in soil?
Next question will be online.
Sure.
All right, the question I have is, in addition to lead, are you also measuring anything like zinc? The specific concern involves galvanized pipes that zinc is also toxic.
So the question is, are there any other metals that I'm looking for in the water, since galvanized pipes are talked about and zinc is also toxic? So no, this study is focusing on lead. This study so far is trying to stay within the bounds of non-leaded pipes and leaded pipes, since especially so far, a lot of the off-campus samples that we have lined up are not galvanized pipes. So while that is indeed an environmental issue, it is not something that this study is going to delve too far into. Thank you for the question.
Great talk.
Thank you.
I think we're gonna have to move on to our next speaker now. But all the speakers are around for lunch. So the next two presenters will both be graduate students. I would also at this point like to acknowledge the Kane Lodge Foundation. They work extensively with Laura Kissel at the Polar Archives, and they've been generous enough to provide a research stipend for each of the students that are presenting today. I also would invite you, when you go down for lunch, for the first time ever, we have an archival display in the building. Laura's worked a decade to get this in place, but the Kane Lodge Foundation has allowed us to buy a display that allow us to have a lot of the archival materials on display at Byrd and rotate out on a regular basis. So thank you, Laura, for working with them over the last few years to make that possible. The next presenter will be Kay Sung. She's a doctoral student in civil, environmental, and geodetic engineering, and she's advised by Dr. Jim Staggy.
Just point out it, use the mouse so that people on the screen can see.
Okay.
I can't read it backwards.
Yeah. Hello, first and foremost, thank you for giving me a chance to talk today. What I am going to talk about is to capture long-term trends in meteorological drought over the last millennium. You might have heard we had a devastating drought events in west part of United States this year. So this is Lake Oroville, California.
Screen sharing. So, technical difficulties.
Technical difficulty with the screen. I'm gonna officially share it on Zoom. Someone's gonna make it work first.
Yeah.
Thanks for your patience.
Again.
Share screen. Yeah. Yeah.
There we go. That. Do you have an image now? Karina, use. Okay.
Yeah. So this is the Lake Oroville, the second largest reservoir in California. The hydropower at this lake had to stop for the first time ever due to falling lake levels. You can see the normal lake level should be this line, but you can see the lake level drops significantly this year. Before talking about very dry issue, I'd like to talk about myself. I am Kyungmin Sung. You can call me Kay in civil engineering department. I'm a third year of PhD student. So I love nature and being outside with my husband, and that motivated me to study water resources under climate change. I define myself as a hydrologist. I work with Dr. Staggy. So let me go back to my research. This is the Shasta Lake, also located in California. Lake level drops 106 feet compared to 2019. And if you see the drought monitoring map on September 7th, actually October 7th, actually yesterday, and the west part of the United States is experiencing exceptional or extreme drought. So for about those issues, there have been many studies that climate change plays a really important role in exacerbating those severity in drought, especially for some regions such as west part of the United States. But when I tell my friends or other people that I study drought trends, and the climate change is really serious and is causing current drought events, and some of them still doubt and ask me a question, is climate change really affecting to drought events? I understand why they are doubting, because we had this record-breaking drought events long time ago. This is a Dust Bowl events photo in 1930. Just whole family is praying for rain in the long-lasting, devastating drought. And the severe drought also occurred even before the recording period. We can learn that from art pieces. So this painting is made in 1878 in Russia. The people are also praying for rain, which probably a traditional response to drought. So since we had those events long time ago, so I understand people still tackle the question, is climate change, a current severe drought is really a part of climate change? Isn't it just one unlucky event that can happen once in a while? So the simple answer I can say is yes, climate change really shifts the drought trends, but the results can be different depending on what spatial or temporal scale we are interested in. So I want to find a better answer for this question by my research that they're focusing on capturing gradual drought trends of 20th century over the beyond to the last millennium, which is hidden in the extreme occasional drought events. Of course, lots of scholars are already focusing on this issue, so I want to contribute to developing those studies through my research. But before showing you results, I want to talk about what is the drought first. So what is the drought? Drought is simply the prolonged events of deficit of water, but it can have many types depending on what part of a hydrological cycle we're interested in. So this is a hydrological cycle showing the movement of water from atmosphere to ground and then back again. And when we focus on the lack of rain or snow, we call it a meteorological drought. And when this part of words such as surface water, groundwater, or evapotranspiration, if they experience the water shortage, then we define it as a hydrological drought. And if the lack of water impacts on the farming or ecological system, then we call it as an agricultural drought or ecological drought, respectively. In my study, I will focus on the meteorological drought, which is lack of rain or snowfall. So there are many indices to quantify the meteorological drought, but I used standardized precipitation index, which measures the drought severity through just average and normalized precipitation. Especially, I used the 3 months average precipitation because it represents the whole one season of drought severity. So from now on, I will show you the results, but the result shows the 3 months average rainfall, but you can easily think that represents the drought severity. So here is the summer precipitation of May, June, July in Columbus from 1830 to 2020. So I'm showing you the two data sets, GridMet, which is a measured data set, and NOAA reanalysis, the combined observed and simulated data set. So when you see this raw data set, it's a little hard to tell if the summer precip in Columbus is increased or constant. It looks like it's slightly increased, but it's still hard to tell. And also the two data set is not exactly matched because they have their own biases in it. Especially the NOAA data set, marked in blue line, is the simulated results. So it's natural that the data set contains bias in it. So my study aims to capture the trends in those complicated time series and minimize bias between those two data sets. So I will use generalized additive modeling methods, which fits the long-term trends beyond just one linear line, but very wiggly and wavy line, because it better captures both cyclic and monotonic drought trends at the same time. Here's the result of extracting the trends from two separate time series. The bold line here shows the average trend line, and this two thin line shows uncertainty bounds. We can see the cyclic fluctuation since 1900. The observed data shows the similar trends here, but have little higher averages. So you can see this bias exists between two data sets. So I did the additional modeling to have this one remove biases and got the trend line. And you can see the average trend is a little shifted upwards. And also we are living in a very wettest trend since 1960, even though we have a little drier period, but we are having very wetting trends since 1960. So right now I would like to ask you one question. So what if the trends that we just saw is just tiny part of the whole history? So what if the Columbus was much wetter back in the day and climate is just shifting to the drier regime? Or what if the current wetting trend is just part of natural variability? So, and effects of human activity is very little compared to the natural change. So to figure out those questions and better capture the drought trends and impact of climate change in terms of verifying natural variability versus human impacts, we need to evaluate these recent trends in much broader perspective. So to study past climate, even before people started to measure the climate variables, such as rainfall, we need to use the proxy from natural resources. And as you can see, the tree ring is one of the good proxy data because tree largely depends on moisture during their growing season. So there are a few tree ring related to drought variables are available now, but I will use NASPA data because it publishes last year and it covers up to 2,000 years of 3 months average of precipitation. So I use the data set and merge those data to directly observe data set. So these data start from 300 years to 2020. I use the same modeling techniques to extract trends, and you can see there is unique biases in these 3 different data sets. So I use the same analysis to remove those biases. So here's the final results. This figure really helps to evaluate the current wetting trends of Columbus in May, June, July out of millennial timescale. So we found that the summer rainfall had more fluctuation, is less stable before 1,000 year. And we can see this wetting trends is start from around 1400 years. And these trends become more rapid after 1900, and slope change occurs once again around 2000 years. And it's really interesting to see that we are living in the wettest climate since about 700. So maybe next year, if you have a lot of rain in the summer, just please remind me, Kay. As she said, we are living in the wettest country, wettest period. So I showed the Columbus as we are located in, but this part of country is showing the very weather conditions. So I will expand this study in the future to entire United States and identify a particularly vulnerable region, which is having rapid drying trends. I do believe this analysis will contribute to finding how climate change and human activities affects on recent tandem drought events. So, and I will provide this information to publics and other agents to build resilience to future meteorological drought. So last but not least, I would like to acknowledge that this project is supported by NSF and under my guidance of my advisor, Dr. Stegi, and Noah, who is a data provider, and the Byrd Research Center, who helped me to conduct research and meet many people and provide a lot of good coffees and barbecues and give a chance to talk today. Thank you.
Questions?
What trees are so old around here?
Yeah, actually, I don't know. I just downloaded the data, but maybe my postdoc will know. Yeah, I'll study for it. Yeah.
Will it be easy to find that tree data for the rest of the United States, or is there big gaps that you're going to experience?
So they have this gridded data available. So, but I heard some of the part has much more trees data available, and the other part is not. Yeah.
Other questions from the room? Oh.
So yeah, I see there is quite a lot of noise. You mentioned about trends for humidity. did you evaluate the significance of these trends and how? I see that you are in certain Bayesian approach there. Did you use any statistical methods?
Yeah, I use this generalized additive modeling. That's part of the, regression, and also I calculated parameter through Bayesian analysis. So this Bayesian analysis gives me an idea of a whole distribution of one trend line. So I can see if this uncertainty bounds is very large or very small, depending on the what part of measure or what part of what types of data I am using.
Any other questions? Thank you very much.
Okay, one more question. Any consideration to the trends in the swing between extremes in the hyperstate?
Oh, that's so now I'm working only on trends line because to see the gradual trends. Yeah, but there are many studies that focusing on very extreme drought, but I think it's a little different story that I am working on.
Any other questions? Thank you very much. And our last student presentation today, being Madeleine Lomax-Vogt. She's a doctoral student in the School of Earth Sciences, advised by Paolo Gabrielli and John.
Yeah, so the, yeah.
Any questions for me?
Yes. Is there interviews or not? Yes. That because you're probably going to use the mouse anyway. Hide these controls.
Take your time. Okay. Thank you.
There you go.
Yeah, thank you.
Yeah.
So I know I'm the last person between you and lunch, so I will keep going. My name is Madeleine Lomax-Vogt, and I will be talking to you about our work characterizing atmospheric nano and microparticles that have been entrapped in ancient and modern glacial ice. So in particular, samples from the Taylor Glacier in East Antarctica and the Mount Ortles core in the Eastern Alps in Italy. A little bit about me. So funny enough, I'm from Northwest Ohio, so I wonder how much phosphorus I've consumed over the last few years. I left Ohio and went to New York to get my bachelor in chemistry from Alfred University, and then I came back to the homeland to do my master's and PhD with Dr. Paolo Gabrielli and John Lisek here at OSU. Outside of science, I like to be involved in the community. I'm very involved in state and local politics here in Ohio, and I'm also a big sister for Big Brothers Big Sisters. And that's a big part of my impetus for doing this research. I think it's really important as scientists that we are active in our communities and our political systems to make sure that there's good science being legislated. Beyond that, I do want to point out, I have some really cute little pets waiting for me at home after this presentation. So that's a lot of what I spend my time, 2 rabbits and 1 cat. So why are these atmospheric nano and microparticles important? Well, if you see here, sunlight hits the earth and there are these particles in the atmosphere, and we care about them because they impact the amount of sunlight that actually reaches and warms the planet. So particles can absorb light, so it'll take that heat, that sunlight in. They can actually scatter light in and out. So if light is scattered out, it cools. If it's scattered in, it'll heat the earth. And they also act as cloud nuclei. So again, light can be scattered in or out from these particles. And why is this important? Well, the number the size and the mineralogy, so what elements are in these particles, is really important for us to understand the amount of the sun's energy that reaches the earth. So how much are we warming, how much are we cooling, and how does this impact it? So what we are doing is we are looking at atmospheric particles over historical time. And our goal here is to determine possible sources. So where are these particles from? Are they from human activities? Are they from fires, mining? And how are these particles linked to our changing climate from the past to the present? And so you can see here in this picture, this is actually some layers, and the atmospheric particles are entrapped into these layers. They're deposited and entrapped. So ultimately, we are using this glacial ice, and it's actually, we're getting a lot of it, or all of it, from the wonderful ice core repository at OSU. If you haven't had a chance to check it out, it's a really cool part of the Byrd Center. And glaciers, as you go down, are older because that new ice deposits on top. And so we're looking at these particles over time, specifically again from Antarctica, which is this really clean ice, sort of the cleanest ice in the world. Very little human activity, hopefully reaching there. And then Mount Ortles in Italy, which is right around human settlements. And so we're using all of this ice to look over time to determine how these trends changed, how the particles changed. And what you can see here is that we can take these cores and you can determine these big events over time. So that dark line there, this gray line here, is actually from a volcanic eruption around 21,000 years ago, and it's entrapped in that ice. So what are micro and nanoparticles? Well, to give you some perspective, this is a TEM, so transmission electron microscopy, so a microscope. This is an image of one human hair. So think about a hair on your head. This is a really expanded image. And it's about 5,000 nanometers, 50 micrometers across. The particles we're looking at are much smaller, so they can be around 0.1 to 100 micrometers, or even smaller, these nanoparticles. It's that really, really small pink dot there. So we're trying to look at all of these micro and nanoparticles that have existed in our past atmosphere. And what are these particles? Well, we have the microparticles and the nanoparticles. And often in science, you'll see the use of engineered nanoparticles. These are particles that we've made, and they're usually this sort of uniform shape. You can see in this picture, they're pretty spherical. And they're in clothing, they can be in sunscreen. These are some common applications. There are also these sort of natural or anthropogenic particles. These are particles that are produced by nature or produced by human activities. Often they have an irregular shape, and they can come from ocean vents, so that's a natural process, or metal refining, a human process. And we're trying to measure all of these particles, both large and especially the small particles, those nanoparticles. So why is this important? Well, right now, a lot of the modeling that we are using to model climate change assumes that these atmospheric particles, these dust particles, are a uniform composition. So one of the things we know about minerals is that different minerals will reflect different amounts of sunlight. So some minerals will reflect more and some will reflect less. And we really need to know how many of these particles are there and what are they made of. And when we look at what particles actually are in the atmosphere, we see that they are much different. They're varied in composition and size. And so these plots over on the right here show 3 of the individual nanoparticles that we've measured from these glaciers. So the top particle, particle 1, you can see has titanium and iron. We detected those elements in that particle. The next particle underneath, we only saw potassium. And the third particle, aluminum, silicon, potassium, iron. And so these 3 particles shows you these particles can vary tremendously in composition and size. And we are able to measure thousands of these particles. So this gives us a huge amount of data to look at and make these bigger, have more rigorous statistical data in terms of understanding the composition and the number and the size of these particles. And this is actually cutting edge research. I was actually at CMU, Carnegie Mellon, yesterday, using their one of their instruments to do some of this research, and hopefully we'll get one of those instruments here one day. But it's very cool research. This is sort of one of the first applications that's been using it in this way. So something that you might connect to, we heard about lead a little bit ago. What's the lead like in the atmosphere over time? So our instrument, our technique is able to measure the amount of lead in each individual particle in these samples. And so this first plot here shows the amount of lead on the x-axis, that horizontal axis, and on the vertical axis, it shows the number of particles per milliliter that contain that. So not too many particles. This is about 32,000 years old, this ice. We can then look at ice that's about 8,000 years old in the Holocene period. And again, not too much lead, maybe a little bit of a change. However, once we move into this sort of pre-Roman, humans are starting to do mining and agriculture, and we start to see an increase in the number of lead particles that are in the atmosphere. And if we move to this sort of post-Roman period around 670 AD, far more lead containing particles, far more lead in the atmosphere. And this is due to, again, increased mining, increased human activities on our planet. If we move even further in history to around 650 AD, right before the Industrial Revolution, right around, again, more lead particles in the atmosphere. And then if we move to the modern era, we see these lead particles still in the atmosphere, probably from leaded gasoline or, again, mining. And I think what this data really should tell you is that humans impact the environment tremendously. We can see before humans started to really produce and have this sort of industrialized behavior, we didn't really see too much lead in the atmosphere. And now we see lead from our behaviors. And so it's critical that we understand these changes over time in the past so we can determine what's happening in the future. So I think the takeaway from this should be that, first of all, these atmospheric particles that have been entrapped in the glacial ice can again be traced back to these human and environmental sources. And in particular, we want to sort of focus on like, how have we impacted these changes over time? What does this tell us? And the second thing is that because we are able to measure the number, the size, and this mineralogy of the particles, two mineralogies, it's really important. Sorry about that. Of these thousands of particles, we're hoping to help climate scientists who are doing this modeling make their models of the past slightly more accurate to help us understand what happened in the past and then what is going to happen in the future. Now, of course, I didn't work on this project alone. We have a tremendous amount of support, not only at OSU, at the Byrd Polar Center, but also at Carnegie Mellon. And we were also funded using 2 NSF grants and then some outside money from research institutions and industry. Thank you so much, and I'm happy to answer any questions. Yes.
That's a very nice presentation.
Thank you.
I have a question. So you're looking at individual particles. At some point, you need to try to answer the question, some of the questions that all people be asked. You're going to have to scale that up.
Yes.
And so how do you go about extrapolating what you've learned from a few particles to the large number of different particles that a sample from virtually anywhere, just pick your favorite place, you have?
So the question is sort of how do we use what we're developing now to then apply it to these larger data sets? So this is a good question. We've only really looked at a few ice core samples so far. You could see it back here in this sort of lead slide. So our goal is to develop these methodologies to take data using, it's called single particle inductively coupled plasma time of flight mass spectrometry. It's a lot of words that essentially means that we can look at all of the elements in one particle. So hopefully what we're doing is developing these methods where we can melt an ice core, take the data, and then sort of use these data applications that we're developing now to figure out what's in these particles. So my work essentially is characterizing these individual particles, and we are very early in our method development, but we do have plans to measure about 50 more samples, hopefully once we know that our methods are sound. Does that answer your question? Thank you. Yes.
Thank you. That was great. Really
Thank you.
clear, great presentation. I'm curious. I really like the premise, your interest in public policy.
Yes.
And cats.
Yes.
I'll leave the cats aside. I like
Well.
cats. But this is really interesting to see the inadvertent addition of particles to the atmosphere. As we look to a warmer world where policy spaces are including geoengineering, what do you think about that?
So the question is,
in terms of putting aerosols purposefully in the atmosphere to cool the planet, because we're not able to restrict the emissions of greenhouse gases.
That's an excellent question. So the question is essentially, what are we going to do if we're adding aerosol into the environment in this modern age?
Yeah.
That's a good question. I don't think about modern ice too much, I'll be totally honest, in the atmosphere. So I mean, it would depend on the types of particles that are being added. So really, we're only looking at particles that are insoluble. So they're not going to dissolve once we melt these ice cores. So if they're in the atmosphere, there are some techniques that sort of can take this air in and measure all the particles. And the reason they can do that is there's such a large volume of sample. We're working with very little sample. So I would guess that they are going to have to adjust and account for those changes as we make them. That I'm sure the data will change, but I think it would depend for this particular research on the types of particles. So if they were iron particles, for example, I've read about iron seeding, and these particles have a higher refractive index. You know, we would have to account for that when we are measuring these samples moving forward. Does that answer your question? I'm not super familiar with what we would do now, but that's something I'm going to think about.
Yeah.
So I have two questions.
Okay.
So the first question is, could you please explain the plots on the bottom? What is the mass?
Sure.
Femtograms of lead.
Sure.
And then also, while you're explaining that, you also explain the source of these particles.
Ah, that is an excellent question. So to start, the first question is, what is this sort of mass femtograms of lead? So this is just telling you a femtogram is 10 to the minus 15th grams of lead. If you see this second label down here. And so that is just telling you how much mass, how much the amount of lead in each of those particles. And then these bars sort of sum up all of the masses in that particular bin. So if you look here, all of these particles in this bin that says 0.1 are going to be within a certain range, and we just sum up all those masses. The sources, that's a good question. So that's sort of our next step is looking at the composition of these particles, looking at what elements are in them. Can we then go back and say, given its time period, given what we know about atmospheric transportation, so where does the wind take particles from a fire and where does it blow them? Our goal is to sort of backtrack. So we have this particle information, and then going backwards, where could it have come from? So for example, if we think about some of these plots here in the middle, this sort of post-Roman and pre-industrial plot, we might assume that a lot of that lead is coming from mining, for example. And then once we get into 1955, a lot of that lead we would suspect is probably from leaded gasoline. So we sort of have ideas of where this is coming from, but I think our next big step is to then determine, you know, what are the sources.
Thank you very much.
All right, thank you.